Hello everyone. Welcome to tonight's session on synthesis and multi-step reactions. Let's jump on over here. Before we begin, let me know in the comments where you're tuning in from and when you're taking your Orgo final exam. If you're here for something different that is still going to require organic chemistry, like the MCAT, the PCAT, the GAMSAT, let me know. And let's see, Noelle, it is good to see you. I'm going to miss you after your final, Noelle. Over the course of the semester, I start to recognize more and more names. And so it's nice to see familiar, I was going to say faces. I don't see your faces, but it's nice to see familiar names. Hello to, this is Terry. Is this Terry or somebody else? Just trying to see if I remember who's who. He based as my face is that. Eric, I'm not sure I understand what you're saying. Adriana from Florida, also testing early December 11th. We've got Wisconsin 12th. Hello. All right, Terry, it is good to see you. Brian from Florida, it is good to see you as well. I will be heading to Florida on vacation very soon. So if anyone has good tips on what to do with an almost 4-year-old, I'll take all the advice. And more comments coming in. Third midterm, December 3rd and final on the 12th. I don't like when professors do that. You should have an exam and then plenty of time to learn new material or review before the final. Don't give them back to back. What's the point? Brian, thank you so much. I appreciate that very, very much. Okay, so let's say we jump in and look at today's topic for synthesis and multi-step reactions, because up to this point, you have learned a lot of different, here's a reaction, here's a product, here's a reagent, here's how we do it. Then on your final, you're given something like this. And yes, this is an organic chemistry 1 beginner synthesis problem. And you have to figure out, well, how do you come up with the steps? What are all the intermediates? What are all the reagents? How do you start with a problem like this? I forgot to tell you, we are going to cover a lot today, so do not worry about writing down all the notes. If you've been on a workshop before, if you've been on live stream, you know the drill. Just put live notes in the comments, and I will give you a link to grab tonight's PDF notes, which I send as soon as I'm done. Well, a little bit after I'm done. If you're watching the recording, it'll be automated, same link, and you'll get access to the notes. On your Orgo final, you will be faced with something like this and asked to come up with all the intermediates, all the reagents, all the everything in between. And this is where a lot of students panic. So my question to you is, how do you begin a problem like this? I see a lot of students take this and start with the reactant. Maybe I have my first step. What do I add to it? I see some students will do the exact opposite, and they start with a product and work their way backwards, right? Retrosynthesis, working backwards. I have students who will start writing everything that they know and hope that somewhere along the line, everything kind of fits together. I'm going to argue that the way to do a problem like this is not this, not this, not this. This is going to lead to confusion. This leads to writing everything you know until you get stuck. It does not help you get to the product. The thing is that this worked early on when you had molecule A and you had to come up with molecule B, and maybe even molecule A goes to molecule B goes to molecule C, where you had to fill in something here and here. But by the time you have learned multiple reactions, multiple chapters that you're able to put together, most Orgo students at the Orgo 1 level will have covered at least alkenes, alkynes, substitution, elimination, maybe radicals, maybe alcohols, maybe a couple more. And so now on your final, what you're going to see is molecule A, like I gave you, but molecule Z, you have that many steps in between, and you have to come up with everything. So how do you approach this? If you can find a way to simplify it. So I'm going to show you this in action in a moment. First, we'll kind of talk about the big picture. If you can simplify this, so molecule A, I know at least goes to molecule B, and I know that Z came from Y. Now I have a smaller synthesis to put together. And what if I could take this one step further and say B goes to C, and I know that Y came from X. Now I have even less to come up with. And the more I can have my products and reactants kind of merge in the middle, the less I have to be overwhelmed about. But more importantly, and hello, I saw hellos coming in. More importantly, the key is to figure out how to unlock your brain, because on a final, if you panic, if your mind goes blank, that's it. Nothing's coming to you until something jumpstarts it. And so what I want to show you today is actually a very simple method to jumpstart your brain. So let me know in the comments if you find that your mind goes blank, and even though you know the material, once you freeze, it's very, very hard to get to that next step. And if yes, let me see a fire emoji in the comments if you want to see how to get out of it, because it's not just about knowing information. It's about doing busy work. Instead of trying to think of all the difficult and complicated reactions and things that you know, what if you can get your brain going with something so small and so simple and so straightforward that it doesn't require you to panic? And once your brain starts going, once you get in the zone, then things kind of start flowing. And at that point, it's very easy to start thinking about, okay, what are all the reactions I know? And the busy work for a synthesis problem is very, very simple. I want you to ask yourself 2 questions. And these questions, you can literally mark up your molecule to find the answer. So it's not going to require a lot of extra thinking. Question number 1, you're going to ask on any synthesis problem, what's the same? And question number 2, you're going to ask what's different. I don't want you to memorize a million things to start. This is all you're looking for. This is the busy work. And if you can get your brain going in this direction, you will find that it wakes up a lot faster and the answers will fall into place. And if you're not sure, give me a chance to prove it to you. What am I looking for specifically with what is the same and what's different? I'm looking for the number of carbon atoms. You will be amazed at how many times I've seen students lose points because they forgot to count and realize that I should have added a carbon here, or I should have added 2 carbons there. They just didn't count how many carbon atoms. The next thing you want to look for are the functional groups. And when I say functional groups, I just mean anything on the molecule. So a halogen is technically not a functional group, but I'm also looking at that. And the third thing I'm looking for is what I call the POR, the position of reactivity. And this is where we have something that can react on the molecule. Because if I don't have something to react, if I don't have a leaving group, if I don't have a nucleophile, if I don't have a base, electrons, how am I going to make a reaction happen? These are the things that I'm looking for. Don't worry if you don't yet know how to apply it. If you think you can at least memorize this when your brain is stuck, give me a thumbs up in the comments, and then I'm going to show you how to use this to answer problems that may look scary like this and are actually not that difficult. Yeah, maybe a little difficult, but I'm going to show you how to make it easier. We'll start with a simple problem just so you can see how to apply it. Say I have a molecule that looks like this, and you're asked somehow, some way to turn it into a molecule that looks like this. In the comments, do you think this problem is easy, medium, or hard? I'm trying to give you something easier first just to show you how to apply the framework that I showed you, and then we'll work our way up. If you're just joining, welcome. Don't worry about copying everything down for today. Instead, just put live notes in the comments, and I'll send you a PDF of everything that you see me drawing after I finish this session. And if you're watching the recording, same thing, you'll get the link for the notes. So we have something like this. We want to start with not the reactants, not the products, not everything we know. We want to start with question number 1, what is the same? And question number 2, what is different? So let's see how to apply it. What is the same? I'm starting with the number of carbon atoms. I see that I have 3 carbons in my reactant, 3 carbons in my product. The fact that it was flipped upside down, it doesn't matter because these molecules can rotate. As long as the carbons match up, we're good to go. So the same is the carbon atoms, or just the chain. And what is different is that I have a bromine on my reactant, an aldehyde on my product at the same position. They both happen on carbon 1, so I don't have to do anything crazy yet. I'll show you that in a different problem. So the question now is, how do I turn a bromine into an aldehyde? It's not a completely different synthesis that I have to think about. I'm just asking, how do I go from bromine to aldehyde? If you know that reaction, let me know, because I don't know that reaction. I don't know how to turn a bromine into an aldehyde. This is not anything I have ever learned. And when you see a problem where you can't go directly from the reactant to the product, instead of starting to think of a million different things along the way, what I want you to ask yourself is, how can I break this into pieces? If I don't know how to go from the reactant to the product, I'm sorry, reactant, you're not serving me. You're dead to me. Just get out of here. Ignore this for a moment. And instead, we'll ask a different question. If I have to make an aldehyde on a molecule, on any molecule, do I know any reaction whatsoever that can give me an aldehyde? At the Organic Chemistry 1 level, because I know most students right now are on Orgo 1 here. In the Organic Chemistry 1 level, you will have learned one of two reactions. Well, you probably learned going from an alkyne to an aldehyde, right? You do the ketone tautomerization from your just breaking one pi bond to get an OH. So that is one. And some students will also have learned oxidation, but I know not everyone, so we'll focus mostly on the first one. So I know that if I have an alkyne, I can then do some kind of alkyne addition reaction. And I'm not worried about the specific one yet. Here's the key. If you're trying to think of intermediates and reagents and mechanisms and everything, you have too much going on in your brain, and that's very easy to get overwhelmed. So I like to take the approach of intermediates first. Once I have all my structures, then I go in and fill in the reagents. For two reasons. One, I have ADHD. My brain is all over the place. Give me one small thing to focus on at a time so I can find my way to the answer. And two, professors tend to take more points off if you miss the intermediates, not as much if you miss the reagents. Put a different way, sometimes, and I will very proudly say I've done this, if you can come up with the intermediates and you forget the reagents, just make something up. Make it look credible, put some atoms in that you know need to be there, and you'll get partial credit because your professor will think they mixed it up. You'll still get partial credit. So with that, we're going to use the intermediates first. We'll have an alkyne with just 3 carbon atoms. And then I ask the question again. Do I know of a reaction that gets me from a terminal halide to an alkyne? And before we answer that, what I did here is we turned this into a different problem. Instead of going from A to Z, now we only have to go from A to Y. It's a smaller problem. This is no longer relevant. And it's going to get a little bit easier and a little bit easier. I still don't know how to go from a bromine to an alkyne. So once again, I'm going to get rid of my reactant and ask myself a different question. Yes, Lori, we want alkyne formation, but the question is, how do I get there? And if I don't know alkyne formation from a halogen, which I don't, I can think of something else that will give me alkyne formation. I do know how to make an alkyne from a dihalide. If I have 2 halogens on the molecule, I can do a double elimination. Not too many carbons. If I do a double elimination, then I can get my alkyne. So this is the idea of working our way one step at a time. We are going to run out of room, so let's do that. And so we're working our way backwards one step at a time using the pieces that you know. Thank you so much. I appreciate that. So we ask the question again, what reaction do I know that will take a molecule that has a bromine and add a second bromine to it? How do I add a second bromine onto a molecule that already has a bromine? If you don't know the answer, if you don't know how to get there, I don't either. This is not a reaction that I know. Maybe it doesn't exist. Maybe I never learned it. Probably doesn't exist. And so we'll ask a different question. If I don't know how to make it from the starting molecule, do I know how to do a dihalide from anything else? How can I take any molecule whatsoever, or can I take any molecule whatsoever and put 2 halogens on it? Well, yes, I can, because I can do a halogenation reaction with an alkene. And if I use something like Br2, I can get the dibromo on there. Okay, so I'm going to pick on this student here because no question is a dumb question. You ask, that is how you learn. Never let anyone ever make you think that a question is a dumb question. So now that I picked on you and we got that out of the way, why did you choose an alkyne for the second to last step? Very good question. Definitely not a dumb question. I was trying to figure out how to come up with a product from the reactant, and I did not know. I don't know that reaction. And so I asked myself, of all the reactions that I do know, is there one that allows me to take anything whatsoever and get a carbonyl out of it and get an aldehyde? And the one reaction that I know at the Orgo 1 level that gives me an aldehyde from something else is an alkyne reaction. And that's why I did an alkyne, because what I'm trying to do is ask myself, if I need an aldehyde, where does that come from? It comes from the alkyne. So one step back, I have an alkyne, which came from a dihalide, which came from an alkene. And finally, let's go back to our starting molecule and ask the question again. Do I know of a reaction that will take my alkyl halide and turn it into a molecule that has an alkene? Yes. And yes, that was correct. I saw it earlier, but I didn't get a chance to comment. That is correct. So now that I have all my steps, let me just fly back through and verify. I take my alkyl halide and I eliminate it to get an alkene, which I then do an addition reaction to get the dihalide, which I then do a double elimination to get the alkyne, which I then do a hydroboration to get the aldehyde. So now that I have it all there, let's go ahead and fill it in. Now at this point, as we're going through it, if you find yourself uncomfortable with some of the reactions that come up or some of the reagents, I will try to specify what chapter or what topic it comes from so that you can go back and review. Because for your final, you need to know how to tackle synthesis, but you also have to know the individual reactions. If you need help with the individual reactions, I have something for you, which we'll talk about at the end. And so that way I've got you covered regardless. All right, so looking at what we have here, if I have a bromine, that's a halogen, I'm turning it into an alkene. This right here is an E2 reaction. We can also do E1, not necessarily for the primary, but in general with synthesis, I like to use E2 because I like to do my SN2 and E2, so I have no carbocations, no rearrangements, no questionable side products. I just E2, SN2 directly what it is that I need. So this one, I'm choosing E2. And the reagent could be any strong small base. So for example, NaOH, H2O. I can add heat. I don't have to. I'm good to go. Once I have the alkene, I'm going to do an alkene addition reaction. So this is in the alkene chapter. And I'm simply going to add something like Br2 or Cl2 with a dihalide. I'm trying to do reagents in red. So let me try to remember that. I'm going to use Br2 and something inert like CCl4. Once I have my dihalide, I want to do the double elimination. This one is in the alkyne chapter. This is alkyne formation. And I want to use a very strong base, not any E2 base. It has to be a very strong base. So we'll use NaNH2 in NH3. Now this is a tricky one. That's step 1. Step 2, I have to follow it up with some H2O. Otherwise, I will get an unexpected product. Let me show you. If I have my product formed, and don't forget, we have the terminal hydrogen. If I still have NH2 minus in solution from the NaNH2, this will get deprotonated, and I'll get my alkyne with a negative charge, which is great if I want to do chain elongation, but not for this product right here. And so if I add H2O, that will get protonated. The negative charge will grab one of the hydrogens off of water, and that will reprotonate the alkyne. So even though it doesn't look like anything happened, you do need that extra step. Otherwise, you're going to get something completely different. And last but not least, once we have the alkyne, we're going to do hydroboration. I've seen many different reagents or many different versions of boron here. I think most professors stick to something like B2H6, so I'll draw that one here. B2H6, THF, NaOH, and H2O2, just like your alkene reaction, but we changed boron into B2H6 instead of BH3 because it's a little bit more stable. All right, that was a lot. So let me know if you followed along with the reaction, but more importantly, if you're comfortable with what I did here. What is the same? What is different? And if I don't know how to go direct, what questions can I ask to give me clues, to give me intermediates, so that I can kind of sort of slowly make my way there. A question: do you have to specify the NH3 liquid? If your professor is picky like that, then yes. So technically this is a liquid, but NH3 is liquid. So I don't know. I haven't seen professors take off for that. NaNH2 alone, if that's what you're asking, I have seen some professors do that as well. I would put the NH3 though, just in case. For the second step, can we put H3O plus as well? Yes, same thing. It's going to be just about protonation. You don't want a very strong acid though, because a strong acid will give you a hydration at the Markovnikov position for a ketone, and we want an aldehyde. Now, this is not going to go directly to the aldehyde. It's going to give us an enol intermediate, but then the enol will tautomerize and give us the aldehyde in this case. Can we use 9-BBN? Yes. So 9-BBN, let me write them out here. So we have BH3, B2H6, 9-BBN. What do they all have in common? It's a boron for hydroboration. It's just a matter of which one you learn. A couple of students learn the 9-BBN, B2H6, I think is the most commonly taught, but all of them are correct. Question: can you show the mechanism for step 3? We're not going to go into mechanisms today just because I want to get through quite a few synthesis. Step 3, 1, 2, 3. This one right here. So I'll just kind of fly through it. What happens is you have a hydrogen here, a hydrogen here, and a hydrogen here. Each time you bring an NH2 minus in, the NH2 grabs the hydrogen, collapses, kicks it out. It almost looks like an E2 reaction, except it happens to both hydrogens and both bromines, and then the third one just gets grabbed off. Can we just write R2BH? R2BH is an intermediate that forms in the mechanism. I haven't seen it taught as this is the reagent, but if your professor taught that, then go for it. All right, so let's try another one. What I am doing in showing you these reactions is I'm trying to focus on somewhat simple problems to demonstrate the steps, to demonstrate this is how you think about it, this is how you approach. But once you understand it, the only way you're going to get really good, of course, is to do lots and lots of practice, way more practice than we're doing here. And so after so many people asked me for practice, I went and wrote a synthesis practice exam, an entire exam just on synthesis practice. It's not available on my website, but if you've been to my workshops before, you know I give you exams, worksheets, quizzes, all the good stuff. Just put, what should we put in the comments? Put exam in the comments, and I'll link you to grab the synthesis exam. A couple more questions. For NaOH, H2O2, can you put H2O2 and OH? Yeah, that's the same thing. So NaOH, the Na is just a positive spectator, and so the OH minus is all we really care about. For the last step, can we add water and next react it with mercuric sulfate? So if you're using mercuric sulfate, you're going to get a ketone. That's a Markovnikov addition. Same everything, but Markovnikov versus here we want anti-Markovnikov, and that would give us a different molecule. But if the goal of the reaction was a ketone, then yes, that is what you're going to put. Just grab that link for you. All right, I mentioned that there was another way that you could have done it. So let me just grab this again. The next one is going to be a lot easier. So let me know in the comments if specifically Orgo 1 students, if you already learned redox, because I know some do, many don't. I didn't learn it until Orgo 2. If we're looking at something like this and redox is in our arsenal of reactions, then asking the questions, what is the same, what's different? We determined we don't know how to go direct. What you can ask is, how do I get an aldehyde on a molecule? I know that I can get the aldehyde there from an alcohol. If I have a 3-carbon chain and an alcohol at the end, I can very easily oxidize that alcohol to an aldehyde. And that means this is a much, much simpler reaction, because in one step, I can turn that bromine into a terminal alcohol. So if you've learned redox, this is a much easier way to do it. Let's go ahead and fill in the reagents. To go from the bromine to the alcohol, we are looking at an SN2 reaction. For SN2, we want to use whatever you see on the molecule having added. That is your nucleophile. So we'll do NaOH. Just make sure you change it up. Your solvent has to be polar aprotic, so you won't have an E2 reaction happening by mistake. Once you have your alcohol, you want to oxidize it. This comes up in different chapters, so I'm just going to put oxidation, and wherever that chapter is, that's what you want to review. Because we're going from an alcohol to an aldehyde rather than a fully oxidized carboxylic acid, make sure you use a weaker oxidizing agent. So we'll use PCC, pyridinium chlorochromate, because this is a weaker reagent that will stop at the aldehyde and not go all the way to the carboxylic acid. The way I remember it, this mnemonic comes from one of my students. PCC starts with a P. It's a prude. It doesn't go all the way. That's how you know it stops at the aldehyde. All right, let me see some hearts in the comments if you're liking this approach so far, and absolutely correct. Noel, we didn't learn that reaction until organic 2. Yeah, a lot of students don't. Radical polymerization, that would definitely be Orgo 2 as well. Question. What is PCC? My professor hasn't taught it to my class, but I see. Yeah, so PCC is pyridinium chlorochromate. Chromic acid and a lot of the reagents related to it with the chromium are used as oxidizing reagents. PCC is almost like a blocked reagent where it doesn't get to work as strong. Just think of it as an oxidizing reagent that did not get enough sleep, did not have enough coffee, and is just not able to put in 100%. So it only does a partial oxidation. The link doesn't work for the exam. That's not good. Hang on, let me check. Is anyone else having trouble with the link? It just opened on my end, so let me see what other students say in the comments, because the link is working for me. Wow, Joe, that is, ouch. Okay, I'm seeing that it works. So if it's not working for you, but it's working for everyone else, how did that heart get on there? I don't know how to remove that. Let me try something. Okay, that pulled it down. Okay, it's working now. Excellent. Yeah, I want to make sure that you're able to do the practice. All right, so we have a general approach for how to break down the synthesis, and we'll do more problems so that you can get more comfortable with it. But a question that comes up as we go through this, especially when you have so many reactions, is how do you study for something like this? Because studying by chapter is not enough, right? When you have an exam on 1 to 2 chapters or a quiz on a single chapter, you could study the chapter and get really good. At this point, though, I'm going to recommend that you study by functional group. And this is a really, really good practice exercise to test yourself on what you know and to see how you want to see if you're comfortable making all the connections, because if you can see those patterns, you will have a much, much easier time being able to answer the questions that come up in your exam. So what do I mean by study the functional group? Let's take any molecule. Let's take an alcohol, right? So ask yourself, what do I know about an alcohol in terms of reactions to get there, reactions I can do with it? Well, how many chapters have you learned that will allow you to form an alcohol? You have learned how to make an alcohol from an alkene. You've learned Markovnikov and anti-Markovnikov. You've learned how to make an alcohol from an alkyl halide, your SN1, SN2 reaction. If you've studied redox, you have your reduction. If you've done advanced alkene reactions, you would have done epoxidation, opening the epoxide. So each of these can be converted to a different type of alcohol. Now you have your alcohol. What can you do with your alcohol? Well, obviously you can go and reverse to each of these. So practice this, write it out. How do I go from the alcohol back to the alkene? Internal alkene, terminal alkene. How do I go back to an alkyl halide, terminal or internal? How do I oxidize it to a carbonyl? How do I turn it into an epoxide? That's a tricky one, but I want you to challenge yourself to try it. What can I do with that alcohol? Well, I can do an oxidation reaction. Again, if you've learned oxidation, if you haven't, obviously skip that step. Once I have that alcohol and I oxidize it, my Orgo 2 students, you're back to your carbonyl. You have another carbonyl, but you can go even further, a carboxylic acid. Orgo 2 again, you have a carboxylic acid. You can now turn this into a carboxylic acid derivative. I can't even speak. And how many things can you now do with that derivative? You could do so many things and so many reactions. The alcohol, you can also turn it into something like, I don't know why I did that. You can turn it into an ether, an OR group. You could turn it back into a halide. So take each of these, take the alkene. What can I do with it? Take the alkyl halide. What can I do with it? If you can practice doing this without any question, just take a random molecule, write it out, try to turn it into 5 different things. Turn each of those into a couple of different things. You are going to get so much more comfortable with reactions than just memorizing or studying the chapters. Now, as you're going through this, what you want to look for are your patterns. If you've watched my videos, you know I love my patterns. I love my shortcuts. I love my clues. So I'm going to show you now a couple more synthesis problems, specifically identifying patterns that you can then rely on your exam. Because if you recognize, oh, this has to be this kind of transformation, you don't have to think about it anymore. You know exactly what to do. So let me know what you think of that experiment of just studying by functional group. And meanwhile, I'm going to draw the next problem. And I want you to let me know in the comments if you think this is easy, medium, or hard when you have to convert this molecule into something like this. And where do you even begin? Oh, I see what I did. I see what I did. Okay, I fixed the link in my notes. So today I'm going to focus specifically on beginner problems because I know that I have students here. Actually, let me know in the comments, Orgo 1 or Orgo 2. And Orgo 2 students, the same framework applies, but I'm going to stick mostly with beginner problems because I know that we have more Orgo 1 students present. Lexa kind of asked me, email me, and I'll explain that to you in more detail. All right, so for this problem right here, the first thing we're going to do is not start any kind of reaction. We're going to take a step back and ask the 2 questions anytime you have synthesis. What are those 2 questions? Question number 1, what is the same? And the same is my carbon chain and the fact that I have bromine. But question 2, what is different, is the fact that bromine moved. Bromine went from carbon 2 to carbon 1. And the question is, how do I move a halogen or any kind of functional group from one position to another? This is what I call the move the functional group pattern. So anytime you see something moving on your exam, immediately think of moving the functional group. The way that I move a functional group, it's not one simple reaction. I need to take the functional group off. And I know bromine is a substituent, not a functional group, but we're going to call it functional group for now. I need to take the substituent off and then put it back on. That is the pattern. That is how you move it. And the way you take it off is elimination. So the first thing I'm going to do is eliminate to get bromine removed. That would be with an E2 reaction. but I want to make sure that I eliminate in the direction of the less substituted carbon, meaning I don't want my standard Zaitsev product. I need the Hofmann product. And so to do that, I'm going to have, we're not going to talk reagents just yet. We're just going to keep that in mind. That will give me an alkene. Once I have my alkene, it's very easy to just put the halogen back. And that is it. So again, the way that you move a functional group, addition, elimination, until you get it to where you need to go. That's the pattern to know. So let's go ahead and fill in the reagents. I kind of started talking about the reaction already, but let's fill it in. Elimination in the direction of the less substituted pi bond has to be with a big bulky base that cannot do your more stable elimination. So we're going to use tert butoxide, KOTB, dissolve it in HOTB, add heat to stabilize the intermediate. Oops. Once we have the alkene, we're going to do an alkene addition reaction. Some students learn this in the alkene chapter. Some students learn this in the radical section or radical chapter. So I'm going to give you both. And the reaction here is the halogenation. We're going to use HBr, but we want to do this not in the standard carbocation intermediate. We want to use this with peroxides so that we get that radical intermediate that will give us the anti-Markovnikov terminal halogen. All right, thumbs up if you like the move the functional group pattern, and 2 thumbs up if you want to do the pattern with a slightly more difficult problem. So let's crank it up a notch. Question, for the first step, can you use T-but OK? Yes. So let me show you what I have here. KOTB is T-but OK, is whatever you want to call it. What am I looking at? It's a K plus positive spectator. That's this one. And then the counter ion is an oxygen bound to a tert-butyl group. So TB, tert-butyl. Professors will write it different ways. I used to find this the trickiest. That's why I teach it this way, so you're not caught off guard. Tert-butyl oxide. That is what we have. So it's potassium tert-butoxide, tert-butyl oxide, potassium, whatever you want to call it. This right here is a triple B, a big bulky base, and it's going to give us the E2 Hofmann product rather than the Zaitsev because it goes less substituted, given the steric hindrance for the bulk. Very good question. Let me know if that makes sense. I see double thumbs up in the comments. So what do you think? Easy, medium, or hard for this next one? Let's see what we have. Question 1. So let's do that. Question 1. What is the same? Carbon chain. 1, 2, 3, 4. 1, 2, 3, 4. I have 4 carbons. Question 2. What is different? I seem to have a chlorine on carbon 2 turning into an alcohol on carbon 4. So the question to ask here is, how do I turn a chlorine into an alcohol and move it over 2 positions? We still have a question on the last one. Really good question. So let me go back. You have to have a solvent because this right here is just a base, and the base needs to be dissolved in something. And so if you have a tert butoxide, you put it into its own conjugate base, tert butanol, which is just the same exact thing with an H instead of an O minus. That's your alcohol, and that's your solvent. Really good question. So let me know if that makes sense. We have to turn the chlorine into an alcohol and move it over. We are going to use the pattern of move the functional group. And then with that pattern, I want to go back to this problem. In this case, we move bromine. But who said we had to put it back as bromine? When you move the functional group, you can put any substituent or functional group on there. Once I have an alkene, I could have put an alcohol. So that part is actually pretty straightforward. I just change what I add. And how do I move it over 2 positions? I don't. Remember that the molecules can move around and rotate in space. So who said we had to number them the same way just because it's drawn that way? What if instead I just choose to number it 1, 2, 3, 4 in this direction? Now I just move the chlorine from carbon 2 and turn it into an OH on carbon 1. And that's a pretty easy problem. Step 1, eliminate chlorine in the direction of the less substituted carbon so that it goes terminal. And step 2, just turn it into an alcohol, an anti-Markovnikov alcohol addition, and we're done. That is it. So what reactions do we have here? To get rid of the chlorine, same thing as the bromine before. This is an E2 reaction. And then for going from an alkene to an alcohol, this is an alkene reaction. And we're done. So let's fill it in. E2, we've already seen a small base. Let's change it up. NaO, oh, no, wrong one. We want to have tert butoxide because we want, let me write it the other way. You want to have something that will go anti-Zaitsev. I guess that's not really a term, but you don't want Zaitsev. You want Huffman. That's some heat. And then anti-Markovnikov for your alcohol. This is hydroboration, just like we saw with the alkyne going to an aldehyde. For this one, we're going to use BH3, THF. That's step 1. Step 2, NaOH or OH minus, someone had asked before, and H2O2. And that's it. As long as we recognize the pattern, everything else fell into place. I have that on my list. You just had your exam today. Oh man, if only your exam was tomorrow, you could have had today as a review. How did the exam go? All right, let's look at the next pattern. This one will require a reaction that a small percentage of students will not have learned. And so if you have not, just ignore it. But let's see what we're looking at here. Let's keep it simple. No, we can't keep it simple. Simple won't work. Let's do it here. Okay, finally settled on where I want the bromine. How do we do this transformation? Question number 1. What is the same? The same is all my carbons. Question number 2. What is different? What's different is that I have nothing on my molecule and I'm turning it into a bromine. This is a very, very common pattern once you have learned radicals. So let me know in the comments if you have not, because this is the pattern that I call the something from nothing. If I have a substituent, if I have a functional group, I can move it around, turn it into anything. Give me a halogen and I can give you any functional group because I know how to move it, I know how to add it and oxidize it and substitute it and do all that. But if I have nothing on my molecule, I have nothing to substitute, nothing to eliminate, nothing to react. So the something from nothing reaction is when you realize you don't have a substituent to react, the first thing you have to do is a radical halogenation. And with radical halogenation, you go from having nothing on your molecule to having a halogen, for example, a bromine, on your most substituted carbon. Now that I have a bromine, even though it's not where I want it, I can at least start the pattern that I already know, move the functional group. So I can take this right here, I can eliminate it, and once I eliminate it, I can substitute it again, or I do an alkene addition, and then I could turn it into whatever it is that I want. So that's the key, the something from nothing. That is a radical reaction. And now that we have the intermediates, we can go ahead and fill it in. So yes, the first step, this is a radical. And we are going to use Br2 in heat or light. So you'll see it with a triangle for heat, with an H nu, or even a squiggly line to show a wavelength for light. My throat is not holding up for this session. Once we have that halogen, the next step is elimination. We've already seen E2 for something like this. So we're going to use the same reagents. I think we're on the third or fourth time mentioning tert butoxide in tert butanol. And the fact that you're seeing this for the third time, do you feel like it's starting to be obvious and second nature? And, oh, yeah, of course I know how to do this. I just saw it 3 times. If it is, that is how you get confident for your final. If you can see it over and over and over, your professor is going to run out of ways to trick you. And if your professor runs out of ways to trick you, this is radical or alkene, that is how you ace your exam. You want to get that good. And that's why I recommend doing lots of practice. That's why I wrote the synthesis practice exam, which just put exam in the comments and I'll send you a link. And that is how you're going to prepare for your final exam. Let's put the reagents here. We've already seen it, HBr and peroxides. All right, so that's another pattern. Let me know what you think of it. The next one that professors love is, it'll go something like this. Starting with acetylene and any other inorganic reagents, go ahead and synthesize some crazy molecule. Let me give you a tricky one. Let's go with this one right here. Ignore side products in this case. What do you think? Easy, medium, or hard? So the first question, what is the same? Well, I don't know what is the same. I have nothing else. So let's go back to the problem. Starting with acetylene and any other. So I need to start with acetylene. Let me draw it out. Now we have a problem. Is that the product you want? Yes. So we are trying to synthesize this molecule. Can we do the double bond moving in butene? Can we do the double bond moving in? I'm not following. Are you asking about this one or are you asking about the previous question? All right, so what do we have here? What is the same? I have 2 carbons, and I assume that one of these, 2 of these 3 carbons are the 2 carbons. And what is different is that I have +1 carbon being added, and I have a triple bond that somehow goes to an aldehyde. So where do we go from here? The first thing I want you to recognize is that the number of carbons changed. I am going to consider that before anything else because I need to know chain elongation. And that's the pattern we want to look for. Chain elongation in Orgo 1 is just one reaction. It's your triple bond negative that does an SN2 reaction. As soon as you recognize that, you want to ask yourself, where did that happen? Should we make this even harder and say starting only with acetylene? So we're doing chain elongation. Acetylene has 2 carbons. If I'm starting only with acetylene, then I would have had to have another acetylene. But that gives me a total of 4 carbons. My product has only 3. How do I make a 3-carbon molecule from 2 carbons or 4 carbons? Well, what if I go from 2 to 4 and then cut it? So think on that. And let's see how to do it. That's a tricky one. So this is not the kind of thing where I tell you, think of this or think of that. This is a situation where I tell you, this could happen. This is how it's done. Now you know. So this isn't about trying to think of different ways. This is the way that I recommend doing it. If the only option you've learned is chain elongation. Orgo 2 students use a Grignard, and that's a lot easier, but obviously if it's only acetylene, you don't have a choice. So if I know that I will somehow connect these two, I know that when I do an alkyne addition, an alkyne elongation, I will have an alkyne in the product, and that alkyne can somehow be cleaved. So what reaction do I know that will have a cleavage where I cut not only a pi bond, but also the sigma bond? That would be something like ozonolysis. If you recognize ozonolysis, you'll know that what I want here to get an aldehyde, I would have needed an alkene. So one step back, and this is the hardest part of this problem. One step back, I would have had an alkene that underwent ozonolysis. And then the question is, how do I get an alkene from two alkynes? This is a situation where I'm going to leave my products where they are. I'm not going to think about them for a moment. Let me see how to grow my chain and then come back and connect. To grow the chain, I need to have one molecule with a leaving group, the other molecule with the negative charge on the acetylide. So let's take the one and turn it into something with a leaving group. If I have my alkyne, to give it a bromine, I don't know how to do that specifically. So let's kind of jump ahead and say, I am looking to turn it into a molecule that looks like this with a bromine. That would have come from an alkene, which, well, that can come from the alkyne. So once I have that, I'm going to react it with an acetylide. That is HC triple C lone pair negative. That will give me the two carbons, the new bond, and then the green alkyne that added in. And then I can turn that into an alkene, and then I can turn that into an aldehyde. Any questions before we continue? Because this is definitely a trickier one. So I want to make sure you're with me before I start throwing a million more things at you. All right, let's go ahead and fill it in. For the first one, I don't know why I changed the colors. We were doing light blue, right? Let's do it like that. For the first one to go from the alkyne to the alkene, we're going to do a partial reduction. We want to make sure that we don't do it all the way. So we'll use either sodium and liquid ammonia or H2 and a Lindlar's catalyst. It doesn't matter which one because this is not terminal or internal. It's just two carbons. So I'll do H2 and Lindlar's. That is an alkyne reaction. Then to get the bromine, we've already seen this one in the alkene or the radical chapter. So I'm just going to put alkene. We'll use HBr and peroxides. Once I have the bromine on there, we bring this in. The question is, where did this come from? I saw a good question about that. Question, why couldn't we just apply NaNH2 NH3 to the original alkyne to deprotonate it? We are going to for one of the two. And so if we take our original alkyne and we react it with NaNH2 in NH3, that will give me this, and this is going to do an SN2 reaction right here. So that is how we react the second piece. Now we have the alkyne. We want to turn it into an alkene. We'll do the same thing again, H2 and a Lindlar's catalyst. And then for the last step, we want to go from a total of 1, 2, 3, 4 to 1, 2, 3. This is an alkene reaction. And we're going to use ozone, O3 in DMS. Step 1, step 2. Giordano, it is good to see you. And the question is, can we do NaNH2s and CH3I? Okay, that would be allowed, except after I wrote the problem, I said, you know what, let's make it harder only with acetylide. So we can't use anything else as the source of carbon, meaning you're forced to use a 2-carbon molecule and a 2-carbon molecule, making life so much harder for everyone. If your professor gives you this problem but it's acetylene and anything else, then yeah, that's pretty easy. Deprotonated CH3I SN2 reaction and turn it into an aldehyde. Absolutely. What if you had just one acetylene? Well, if you only have 2 carbons, you can't make a 3-carbon product. You have to get another source of carbon. And the question is, what does your professor allow you to use? Hello. I saw quite a few good questions coming in. Let me know if I missed your question or if something still isn't clear. And then I have too many more problems on my list, and my voice is really starting to go. So in the interest of, I don't want to stay up all night coughing, let's go ahead and jump to this one next. This is the one we opened with. And I want your feedback and opinion. Is this easy, medium, or hard? And also keeping in mind, you're going to want to practice, but I want you to think of the busy work, the questions, the patterns, and just kind of thinking through the steps the way we've done them today. All right, ready to make this an easy problem? For the triple bond carbon, is that like that because of SN2, or is that an alkyne reaction? For the triple bond carbon. So this right here is our starting molecule, that's acetylene. We turn it into an acetylide, which is a very good nucleophile, and this is going to do an SN2 reaction. The SN2 reaction specifically is right here. That's the attack, and that is the SN2 product. Can we also go for the double bond moving in an alkene? Email me because this is not related to what we're working on now, and I'm also not too sure what you're asking. So send me a screenshot, like draw it out, send me a picture, and I want to see your question. All right, for this one, let's see if the approach from today can make this ever so slightly more doable. Question number 1, what is the same? We want to look at the molecule and compare reactant to product. So I have this right here, I got most of it, has to be at least this right here. And then we have one more right there. This is the same. I have the green carbons. And then what is different is everything else. So what changed? We had an alkene that somehow turned into a long chain plus an alcohol. That is what we want to take into consideration. And so the fact that I have that alkene, the ring and whatnot, don't let any of that scare you. What I'm looking to see is how I can take a molecule that is an alkene, and notice very specifically, this is the carbon that was the alkene. And I managed to turn one of those carbons into an alcohol, and the other one has all of that added to it. At the Organic Chemistry 1 level, unless you've learned Grignard's, which would also be applicable here, ask yourself, how do I grow a carbon chain? Chain elongation has to be with an alkyne. And so this right here, if I can turn this into an alkyne, then I can add everything else to it. So let's look at the product. This right here would be my alkyne. And then I add this to it afterwards, but I also add all of this to it. If this is the alkyne, that means this right here is a new bond. And if this is getting added, if this is getting attacked by an alkyne, then the carbon that is attached to the what would have been an alkyne, that's where I put a leaving group. That's what I attacked for SN2, and everything just fell into place. Watch. This right here means that I came from a molecule that looked like this with an alkyne right here attacking this portion. So that is 1, 2, 3, 4 carbons, a methyl group, and then a leaving group on carbon 1. 1, 2, 3, 4. methyl group on 3. Let's put a bromine as a leaving group on carbon 1. This right here has a lone pair and a negative. That's an SN2 reaction. That's not quite my product. It's nearly the product. But do you see how this had to come from this a few steps prior? Once you identify the alkyne, that has to get a leaving group. And then the rest is going to be so much easier to fill in. Let me see a thinking emoji in the comments if this part makes sense, because I'm going to then start flying through the rest. Knowing that this is what I want to do, I need to turn this right here into this right here. That means I need to turn an alkene into an alkyne. That is another pattern that I didn't think to teach you separately, so we're going to take a look at it now. An alkene into an alkyne is necessary because sometimes you need an alkyne to do whatever it is that you have to do. And I don't know how to do that reaction. I don't know a reaction that turns an alkene into an alkyne. It seems like a very simple and straightforward problem, but it's not something you can do in one step. So what you're going to do, you're not going to think I need to do this, I need to do that. Just think pattern, alkene to alkyne. These are my steps. Step number 1, get rid of the alkene because you cannot turn it into an alkyne. Turn it into a dihalide instead. Let's do chlorine because I keep using bromine. Then I can do a double elimination of a dihalide. We've already seen that before. That can give me my alkyne, which I then need to deprotonate the terminal alkyne. And I'm going to need more room, so we'll move all of this down here. And let's see where we go from here. Before I continue, alkene to alkyne, alkene, dihalide, alkyne. Let's make sure that we're comfortable with that pattern. And I see questions. My throat is really, really dry. Since the ring is the same, can you call it R and just ignore it to simplify? Yes, absolutely. Big R. Don't worry about it. Life just got so much easier. How did you know it had to be a triple bond? Because I have a chain elongation. So anytime the carbon chain grows, that question is, how does it grow? In Orgo 1, alkyne is the only way you've learned to do that. And so the question is, where was that alkyne? That alkene, these are my 2 carbons. If I have something here, then it had to be an alkyne that I was able to react, grow, and I'm just kidding. All right, let's see if I can make it through just a few more minutes. Questions. Let's see questions. It looks like your 1-bromo-3-methyl-butane is your reagent since it's over the arrow. Yes, that is what I'm adding in this case. This is an SN2 reaction, so we could just put in DMSO or whatever. Most professors won't ask that. They just want to see what you're adding, and that's fine. Bisphenol dihalide, absolutely correct. What if you're only given reactants and you're asked to predict the products in a multi-step reaction? Well, you would also have to have reagents, and then it's just a matter of asking, what does this do? What does this do? What does that do? With these, we do have to worry about reagents from earlier steps reacting with something we didn't want. That is a very good question. How do I put this? We're doing pen and paper chemistry, so I would just think about it as, what are the steps? If you were doing this in lab, yes. For example, you have an acid reaction. Now you want base. You have to neutralize it. You have to extract it. You have to purify it. You would have to do all those extra steps. But for this exam, it's all pen and paper. So if you happen to put something on paper that would explode and take out your entire lab, you're not going to lose points for it because it's pen and paper. We did have a guy almost take out my entire lab once. What was it? He was heating ether on a Bunsen burner instead of a steam bath. It was under the hood, but it was in an Erlenmeyer flask. So, you know, the flasks that kind of come to a point, and then there were just flames dancing out of the flask. Everyone's freaking out, screaming, running for the door. My professor's grabbing the fire extinguisher. My TA, the lab TA, is grabbing the fire extinguisher, and everyone's just panicking. I'm like, guys, hold on one second. I walked up to the hood and went, And I just blew air across the top of that flask. The fire went out. I was a hero for the rest of that semester. Nothing I could do was wrong. It probably helped with me doing well in lab. But man, you almost took out the lab. Well, I guess you wouldn't have, but you know, I almost forgot about that story. That was fun. Question here. Can we also do an SN2 with a carbon double bonded to the O? SN2. You're talking about a carbonyl nucleophilic addition reaction? That would be, if you're thinking Grignards, that would be another way to do it, but I'm not teaching the Grignards now because most students, oh, and that is the next question. Yes, so the Grignard, I'm not going to teach it now because not everyone here has learned it, but what you could have done is this right here came from a carbonyl, that's your Grignard, that is your carbonyl, that's your Grignard, and then everything else is very, very similar. So definitely an option. All right, so let's go back to what we have here. What this will give us, and this is where I kind of want to take the suggestion from the student and turn the ring into an R, because that's a lot. We have the alkyne with a new bond to this right here. Okay, so this is what we have. Sure we have the correct number of carbons, and it does help to number. So we have 1, 2, 3, 4. We'll call this 5, 6. Completely out of order numbering, but as long as we're on the same page, we're good. Then, how do we go from the alkyne to the alcohol? Well, that is very simple, but it's not one step. I don't know how to go from an alkyne to an alcohol, but I do know how to go from an alkyne to a ketone to an alcohol if you learned reduction, or from an alkyne to an alkene to an alcohol. So let's do the alkene version because some of you have not learned reduction. We have 1, that's carbon 6, that's carbon 5, that's the new bond to the piece that we added. And then we have 1, 2, 3, 4 methyl group, and that's our alkene. And that's it. Okay, let's fill in all the reagents. The only reason I gave you this one already is because it's part of what we're adding for the carbons. But for everything else, let's go ahead and fill it in. Okay, so any of the reactions we already did, I'm going to fill in very simply. Cl2 and CCl4 gives us the bisphenol dihalide. NaNH2 in NH3, that's going to give me the double elimination. And it'll also give me this at the same time because this is also NaNH2 in NH3. But because I wrote it out in 2 steps, I'll give you the reagent again. Once we have our product, this right here, this is our reagent. So we have that right there. Then we turn the alkyne into an alkene. We've already used H2 and Lindlar's in a previous step, so I'm going to show you a different one here. So this is an alkyne reaction. And this one is Na in N3. Very different from NaNH2 in N3. It's sodium radical, neutral radical sodium, not spectator ion useless sodium. That does a completely different reaction. That looks drunk. Let's try that again. Alkyne right there. And last but not least, and this is called the dissolving metal reduction reaction, in case you're wondering. And then last but not least, we have an alkene reaction where we put the alcohol on the more substituted carbon. So that has to be a Markovnikov reaction. And let's do H2SO4 and H2O. Pretty straightforward. And these are our reagents. What do you think? Can you see yourself with a couple of practice attempts doing that problem? For the chain elongation, can we use a Grignard? Yes. Let me show you real quick because students keep asking about it. A Grignard pattern, if you see an alcohol, your pattern is this. Take away your OH, the H, give it a pi bond. That right there is where you attacked. That right there was your Grignard. And that's it. This came from an aldehyde and a Grignard. And so if you can recognize that pattern, the Grignard will immediately fall into place and you know exactly what to do. Now, if tonight's session helped with synthesis, make sure that you go and practice so you get really good. If tonight's session helped with the synthesis, though, but you still don't feel comfortable with the actual reactions and reagents that came up, and the idea of going back through everything that you have learned from day one is making you just want to crawl up into a ball and hide because it is so much information to learn. I have got you covered. You don't have time to go back through your textbook. You don't have time to go through a gazillion YouTube videos. And that's why I created a pre-finals crash course bootcamp. So in the bootcamp, you will get very specific, dedicated, these are the sessions, these are the topics you need to know. It's a crash course. We fly through every chapter from day one, not as if you've never learned it, but instead you get it from the perspective of, you probably forgot it, and that's okay. Here's what you need to know for your final exam. Here's what you need to understand. Here are the takeaways. Here are the tricks, shortcuts. This is what you need to look out for on your exam. Quickly, so that you can get through everything in time. If you're on my email newsletter, you would have gotten details about it already. But if you're not and you're interested, the link to sign up is leahforsyth.com/bootcamp. If you're watching this live, there is a special discount available through what day is today? Monday through Wednesday, the 26th. The link is leahforsyth.com/bootcamp. I'll pop it onto the screen. And I'm planning a couple of live sessions. Where did that go? A couple of live additional review Q&A sessions. I'm going to do a couple more on YouTube, but I'll do even more bonus sessions for the bootcamp so that you can get all the help that you need with everything from now through final so that you can ace your final exam. Cover Orgo 1 and Orgo 2. So even though today's focus was mostly Orgo 1, I've got you covered no matter what. Anthony, thank you so much. Once I log off, YouTube will keep me connected for a couple of minutes. So I'll hang out in the chat, get the notes ready for you, send you all those things. And here are the links again. If you need, put exam of the comments for the synthesis exam, live notes for a copy of today's session notes. And I will see you. Well, happy Thanksgiving, first of all, to everyone who's celebrating. And I will see you after Thanksgiving for our next session. Have a wonderful evening and take care. You're very welcome.